Today I'm going to continue through the rest of Chapter 17, talking about Gibbs Free Energy and the third law of thermodynamics. Gibbs Free Energy is defined as G, and it's equal to H minus T times S. So just a reminder, H is enthalpy and S is entropy. So delta G is an expression that tells us how both the enthalpy and the entropy change in a reaction so that we can determine whether it is thermodynamically favored or not. All right, so given the equation here that delta G equals delta H minus T delta S, we can rearrange that from quantities we already know to find out that delta G is equal to minus T times delta S of the universe. And so we already know that from the second law of thermodynamics that delta S of the universe is always increasing for a spontaneous process, so that number would be positive. Since we have a negative sign here with the T, in order for something to be thermodynamically favored or spontaneous, we know that delta G is going to have to be negative. All right, so let's go through a few different examples of delta G and delta H and delta S and figure out whether that's going to be a spontaneous reaction or not, or thermodynamically favored. So if delta G is less than 0, that's negative, and that would be spontaneous. If it's greater than 0, that would be non-spontaneous, or not thermodynamically favored. If delta H is less than 0, that would be an exothermic reaction, which is favored. And if delta S is greater than 0, that would be an increase in entropy, which is favored. So that process would be spontaneous as well. If delta H is greater than 0, then we have an endothermic process, which is not favored. And if delta S is less than 0, that would be a decrease in entropy, also not favored. So if those two values are like that, then this is going to be a non-spontaneous reaction. If delta H is greater than 0, in this case here, then that would be endothermic, so not favored. But if delta S is greater than 0, that would be an increase in entropy. So here we have a case where it is not favored in terms of enthalpy, but it is favored in terms of entropy. And this is one of the interesting ones that you'll almost definitely get a question similar to this on your test. And so what we can say here is that as temperature gets bigger, our entropy term in our delta G equation is going to take over the delta H term. So this is going to be spontaneous at high temperature and non-spontaneous at low temperatures. Okay, we could do the calculation if we knew the values of delta H and delta S to figure out at what temperature it goes from being non-spontaneous to spontaneous. All right, and then the last one, if we have a delta H that's less than 0, that's spontaneous, but a delta S that's also less than 0 is going to be non-spontaneous because that would be a decrease in entropy. So in this case, when we're at high temperature, the entropy again is going to take over, which means it's not going to be favored at high temperature. But if we decrease the temperature, that term is going to start to go away, and we'll find that the reaction is going to be favorable again. So in this next section, we're going to talk about standard molar entropy and entropy changes in chemical reactions. So just like we had standard molar enthalpy in our previous chapter, standard molar entropy is going to be the entropy of a reaction, or the change in entropy for a process in which all reactants and products are in their standard states. And these are the same standard states that we had for enthalpy, so you could look back in your notes to see that, but it's basically 1 atmosphere for gases, the most stable either solid or liquid for pure substances at room temperature and 1 atmosphere, and for solutions, it's 1 molar. Okay, and then we can use this same equation or the same sort of form of equation that we've been using for calculating delta H's of reaction, but this is for delta S. Okay, and so the third law of thermodynamics tells us that the entropy of a perfect crystal at absolute 0, which is 0 degrees Kelvin, is 0. And so the reason I'm bringing this up now is because for enthalpy, we had to arbitrarily set a 0 value because all of our measurements are going to be changes. But for entropy, we do have a value of 0 entropy, which is a perfect crystal at 0 degrees Kelvin. And so unlike with the standard molar enthalpies or the delta H's, like for a gas, for oxygen, O2 at 1 atmosphere, that standard molar enthalpy was 0, but for entropy it will have a value because it's going to have more disorder than a perfect crystal at 0 degrees. So that's just one important difference between those two standard values. All right, so let's do a couple of examples using this equation that I just gave you. So for this one, these are going to look just like the ones we've been doing for delta H's, except now we have standard entropies of reaction. So we'd need to do the products minus the reactants, so it'll be 2 times the entropy of KCl, which is 82.59, plus 3 times the entropy of O2, which is 205.138, minus the entropies for the products, which is just going to be 2 times the entropy for KClO3, which is 143.1. All right, if we add, multiply all those out and add, subtract, we end up with a value of 1,066.8 joules per mole Kelvin. Okay, and then if we do number 2, again, same process. We'll take the entropy for C2H6, which is 229.6, minus the entropies for the reactants, which is going to be 219.56 for the C2H4 and 130.68 for the H2. And then when we add and subtract all of that out, we get a value of negative 120.6 joules per mole Kelvin. Okay, so what you'll see here is that in number 1, we have an increase in entropy, and in number 2, we have a decrease in entropy. And you should have been able to predict that's what the sign would be. So in number 1, we go from a solid to a solid plus 3 moles of gas. And so those 3 moles of gas have much more entropy than the solid would. And in number 2, we have 2 moles of gas in the reactants and just 1 mole of gas in the products. So that's going to be a decrease in entropy in that case. Now we're going to expand this method to delta G as well. So we can do the same thing. The moles times the moles of product minus the moles of reactant times the delta G of reactant will give us the delta G for a reaction as well. So if we consider the reaction that's given here, 2SO2 plus O2 yields 2SO3, we can, given all of the data that's here in this table, we can calculate the delta G of reaction at 25 degrees. So all of these values here are standard, which means they're at 25 degrees. So that's how we would calculate the very first one. So what we have is the moles of product, which is 2 times delta G of SO3, which is negative 371.06, minus the same thing for the reactants. So we have 2 times negative 300.194 plus 0. So for the delta G for O2 is going to be 0. All right, and now we can add all of that together, and we get negative 141.73 kilojoules per mole. And it asks if this reaction is going to be spontaneous, and the answer is yes, because we have a negative delta G. So if we heat the reaction to 125 degrees, why does this reaction become more or less spontaneous? Or does it become more or less spontaneous? And estimate the value of delta G for reaction at this temperature. Okay, so in order to do this, we're going to have to use the equation delta G naught equals delta H minus T delta S. So if we use the same method we did to get the delta H of reaction and the delta S of reaction, I'm not going to go through those because they're just like problems we've done in the past, but we would get a delta H of reaction that's negative 197.8 and a delta S of reaction that is negative 188 joules per mole Kelvin. And so it's important to note that delta S is usually given in joules, and H and G are usually given in kilojoules, but you need them in the same units when you do your calculation. All right, so given those 2 units, we can say that delta G is equal to negative 197.8 minus 398, because that's 125 degrees Celsius. If we add 273, we get 398 degrees Kelvin, times negative 0.188. So that would be converted to kilojoules if I just divide by 1,000. Okay, and when we multiply those out and subtract, we get negative 122.98 kilojoules per mole for delta G. Okay, so this is still negative, so still spontaneous, but it's going to be less spontaneous than it was at 25 degrees Celsius. And we should know this because our delta S is negative, and so if we increase the temperature when our delta S is negative, that's just going to make it the entropy factor even more of a factor in the delta G, and so it will become less spontaneous. The last part of this question is, why is this only an estimate? And the reason it's only an estimate is up here. We say that the delta G equals delta H minus T delta S is true for constant temperature and pressure. But we change the temperature. So this will be close to the value, but it's not going to be exactly the value that we would get at 125 degrees Celsius. But it gives us a pretty good estimate. All right, the last thing that we're going to, last kind of problem we're going to do here is, this is very similar to a Hess's law problem, except now we're doing with delta G's instead of delta H's. So what you want to do is get all of these three equations all lined up so that you can add them together and get the equation that we have up here. The 3C plus 4H2 goes to C3H8. Okay, so let's start with our carbon. Which equation has carbon in it? So we have 3 carbons up here at the top, and this equation down here, our second one, has just 1 carbon. Okay, so in order to get that to add up to the equation we have above, we're going to have to multiply the whole thing by 3, which means our delta G of reaction is also going to be times 3. Okay, for the C3H8, that we can get from this first equation here. However, it's going the wrong direction. It's a reactant in this, and we want it to be a product, so we're going to have to flip that around, which changes the sign of our delta G. And then the last thing we have down here, or the last reactant we have to deal with, is the H2s, and we have 4 in our reaction. This equation down here has it as a reactant, so that's good, but there's only 2 of them, so we need to multiply that whole reaction by 2, which makes our delta G times 2. And so if we add all of these together, our O2s cancel, the waters cancel, and the CO2s cancel, and we end up with the equation that we are looking for. But to do that, now we modified all of our delta G's. So we want to do positive 2074, because we turned that equation around, plus 3 times negative 394.4, because we had to multiply that whole equation by 3, plus 2 times negative 457.1, because we had to multiply that whole equation times 2. So we add all of those together, and we get a delta G for our final reaction of negative 23.4 kilojoules per mole. All right, so that's how you do these. It's just like I said, just like a Hess's law problem that we did in the last chapter. All right, and the last thing I'm just going to touch on is reversible versus irreversible reactions. So a reversible reaction would be one that could go in either direction without the input of energy. And so the formal definition is a reaction that achieves the theoretical limit with respect to free energy. Okay, and an irreversible reaction is therefore one that does not achieve the theoretical limit of available free energy. And what I want you to understand about this is that basically there is no such thing as a reversible reaction in real life. All reactions are irreversible, so if they are thermodynamically favored in one direction, if you want them to go the other direction, then you must put energy in. So that's just one additional conceptual thing that I wanted to mention that ties in with the free energy that we're learning about in this chapter.